Today we're going to be discussing an important application of first-order linear equations to the study of RC circuits. Some of you will have already encountered these objects in Physics 55 or an equivalent second semester physics course in electricity and magnetism. Many of you will encounter them again in upper division physics and engineering coursework. Although we're not going to get into details today, I wanted to just begin by pointing out that there are numerous real-world applications of RC circuits. We're not just studying these for purely theoretical purposes. RC circuits are useful for designing timed circuits, for example in timing the flash on a camera or the windshield wipers on a car. They're also useful as filters, and finally they're used in transformers to help with the conversion of AC to DC voltage sources. An RC circuit is simple to build using a standard breadboard. It consists of two components, a capacitor and a resistor, hence the R and the C. We're going to be supplying a voltage source to our capacitor through this yellow wire here and using a Digilent waveforms generator. And we'll be measuring the output, the voltage across the capacitor, using these two green wires. We'll be displaying the results in an oscilloscope that comes from the waveform software. We're going to look at two examples of input voltages. The first is a square wave, which supplies a constant input of 2 volts for 2.5 seconds, and then supplies an input of 0 volts for the next 2.5 seconds. Take a moment to think about what you think the output might be before proceeding. Are you ready? Well, let's start off by looking at how the voltage of the capacitor looks without any input. It's 0. Surprise, surprise. Now, if I turn on my input, notice that immediately, during this period where I'm supplying a constant 2 volts for 2.5 seconds, the output, this blue curve, starts to rise exponentially fast towards that. As soon as I turn off the 2 volts, switch to the 0 volt input, I can see that the capacitor, the voltage across the capacitor quickly decays exponentially towards 0. These two phases of action are typically referred to in circuitry as charging the capacitor and discharging the capacitor. The second type of input we're going to look at is an alternating current or AC voltage source represented here by a sinusoidal function. We're going to start off with a wave traveling at a frequency of 100 millihertz. That means this wave is going to take 10 seconds to complete in one cycle. If we look at the output in our oscilloscope, recall the output is in blue and the input is in yellow. Notice that for this specific frequency, the output closely follows the input. It has a slight lag or phase shift, as we would say, but its amplitude is almost identical. If I increase the frequency of my input wave to 500 millihertz, notice what starts to happen. We see the size of the phase shift grows, and also the amplitude of the output begins to decrease. This effect becomes even more dramatic if I double the frequency of the input again to 1 hertz, and becomes even more dramatic at 2 hertz, at 5 hertz, and finally the last one we can probably see through this window, 10 hertz. To summarize the results of our experiment, we see that when we supply the circuit with a relatively low frequency input, the output frequency matched and we had very little reduction in amplitude or phase. However, if we increase the frequency of the input signal, then we saw that the frequency of the output signal not only increased, but we also drastically decreased its amplitude and increased its phase. In particular, if we summarize all those experiments by creating a single plot which places input frequency on the x-axis and the ratio of output to input amplitude on the y-axis, then what we would see is a function whose value decays towards 0 as the input frequency increases towards infinity. These sorts of plots are referred to as frequency response functions, or sometimes Bode amplitude plots, and we'll see they play an important role as we progress forward in this course.